In the last lecture, we discussed where geometrical optics is applicable and where wave optics is applicable. Recall that if the size of the slit is much bigger than the wavelength of light, which is tiny. So, if the size of the aperture is much larger, then the light can be can be treated as travelling in rays. However, if the aperture is of the size of the wavelength or smaller than the wavelength, then the light cannot be treated as travelling in straight lines. We have to take account of the wave nature of light, and when we do that, that part of optics is called wave optics. It deals with phenomenon of interference, diffraction and polarization. Then we explained what a wave front is and what are spherical and plane wave fronts. If you remember, if we join points of on the waves of this in the same phase, if we join the points in the same phase and then draw a plane perpendicular to the direction of light, then this plane is a wave front, and lines perpendicular to the wave front are rays. So, this we explained. This is a wave front, you remember, this is a wave front, this is a wave front at a later date according to Huygens principle. Each point on this wave front has become a source of secondary waves, and this is therefore the wave front at a later time. This is spherical, this is a plane wave front, this is a plane wave front at a later time. The distance between them is c times delta t. Then we tried to explain laws of reflection and refraction according to Huygens principle. And today we continue, in this lecture we continue with the behavior of light as waves. Let me show you first a slide in which I have not treated light as waves, I have treated light as particles. What would happen? If I had a slit which had two slits and light comes here, the slits are say a centimeter each, let us say, then what happens? This light goes through and makes the pattern on the screen is exactly the same as of these slits. That is, if I treat light as particles, it is just like if I have a plane here and there is a pattern in that plane, and if I spray paint, then on this surface I will have just the pattern that is on the plane. So, we have got pattern here, and this pattern is repeated on this screen if we treat light as travelling as particles, that is travelling in straight lines. However, in this now we are in a regime where the slits are going to be very narrow, therefore, this picture will change. To do that, we have to recall the superposition principle from the chapter on waves and oscillations. So, I have taken two waves, blue and red. They are of the they are going in the same direction, and at each point therefore, there is if the wave is going like that, a particle is oscillating like this. If another wave is going like this, another particle is oscillating like this, and a particle at this point, for example, will be under the influence of two waves, one going like this, another going like this. So, is under the influence of two waves, and the displacement of this particle would be the algebraic sum of the displacement of the two waves. That is the superposition principle which you have learned earlier. So, this means that each point on the string is under the influence of two waves. These are waves on a string. At each point, the resultant displacement is the algebraic sum of two displacements. Now, I have taken a special case in which the two waves are of the same amplitude and they are in the same phase, this blue and red, they are in the same phase. So, what happens? At each point, the displacement is the sum, that is the amplitude of this wave is twice the amplitude of each of those waves. The amplitudes get added, the displacement at each point gets added. So, the waves are said to have undergone constructive interference. If the amplitude increases, then we say that the waves have undergone constructive interference. Take another case. Now, this red and blue are in opposite phase. They have the same amplitude, but in opposite phase. That means at each point the displacement is 0, this green line. And we say that these two waves have undergone destructive interference. They are in the opposite phase, and therefore, the displacement of each point is 0, and therefore, there is no wave in fact which is the sum of these two waves, and we say that the waves have undergone destructive interference. Now, I am going to show you the same slide which I showed you earlier. There we treated light as particles, and we had just the replica of these two on this screen. Now, we are going to treat this as monochromatic lights, waves of monochromatic light. And now, what will happen? The slits will become sources of secondary waves according to the Huygens principle. So, these are secondary waves from this slit, these are secondary waves from this slit, and they would now interfere either constructively or destructively. When they interfere constructively, we will have a bright fringe here. If they interfere destructively, then we shall have the dark fringe here. So, this will have a pattern now on the screen consisting of dark and bright fringes. If I treat these slits as secondary sources and the light treated as waves. Now, interference of electromagnetic waves such as light waves is due to superposition. Recall first that a source of light consists of a large number of atoms. Each atom emits waves as electron in that atom goes from higher energy state to a lower energy state. So, each atom is emitting waves, but these atoms emit waves not in the same phase, but in random phase. So, each atom emits waves as electrons in it jump from higher energy state to lower energy state. Each atom emits independently, and the emission takes place over a time of order 10 to the minus 8 seconds. Now, if we take two light sources, there will be absolutely no correlation between the emitters. You see, they are all in haphazard or in random phase. All these waves are in random phases. So, therefore, what will happen? If we take two sources of such sources, then they would interfere of course, but the waves will be completely random and highly variable. The interference will take place between such waves, but the constructive and destructive interference will vary with such rapidity that our eyes or any other optical instrument will not be able to perceive changes in the intensity of light. The light from these sources falling on a screen will show only uniform brightness. Let me go back. You see, these are atoms emitting light. They are not, there is no relation between one atom and the other as they emit light. They emit light independently, and therefore, the phases are also random. So, what happens? They would interfere, but the frequency with which you would see constructive and destructive interference of these waves, the frequency would be so high that your eye or any other instrument will not be able to judge the interference pattern, will not be able to see the interference pattern, and therefore, if we have two sources on a screen, if these two sources which are not correlated on a screen, you will see just a patch of light, nothing else. However, for sustained interference, it is necessary that the two sources give waves which have fixed phase relationship. these waves are not, they do not have any fixed phase relationship, they are all independent, their phases are random. But if we have sources which have the same phase relationship for all time, then these sources are said to be coherent sources. And how do you get such sources? Well, here are two examples. You see, these sources, coherent sources, must be derived from the same source, and here are two examples the way you can do that. Here is a point source, these are two mirrors, and the light gets reflected, the light here gets reflected, and they can interfere on this screen. And since they are derived from the same source, they have the same phase relationship, and therefore, you will have a pattern on this screen. Here the same thing, this is a source, and there is a very small, a very narrow point here, and you get rays going in these two directions. They go through these slits, and they can now interfere, and you will have a pattern on a screen placed somewhere in front of them. These are coherent sources. Coherent sources are those sources which have a fixed phase relationship for all time, and for sustained interference, coherent sources are essential. If they are not coherent, then there will be interference, destructive and constructive, but the rapidity with which these changes in the brightness of light will take place will be so rapid that our eye or any other instrument will not be able to judge these changes, will not be able to perceive these changes. Now, you might give an example of a laser light. Laser light is a different thing. In laser light, all these atoms are made to jump from a higher to a lower level simultaneously at the same time, and therefore, all these waves are no longer independent. These waves are generated by atoms, by electrons, which fall together from a certain state to a certain state, and these waves are all in phase. So, this is a difference. Laser light is a source of coherent light. These are all in the same phase. Laser light, is used in the labs these days, very common thing for phenomena on interference and refraction because of this property. They are all in the same phase. It is a coherent source. Now, the classic experiment on interference of light was carried out by Young in the beginning of the 19th century. In this experiment, coherent sources are obtained by projecting light from a monochromatic source on two narrow parallel slits, as I showed you earlier. The light falls here, and then this goes and falls on these two slits. These slits are very narrow, and they then go further and interfere. The waves issuing out of the slits interfere and produce bright and dark fringes. Wherever there is a constructive interference, we have bright fringe. Wherever there is destructive interference, we have dark fringe. So, therefore, on a screen we have the pattern of dark and bright fringes. This is a bright, this is a dark, this is bright, this is dark, this is bright. So, we have a pattern of dark and bright fringes on the screen. Up to this point, say the center of the screen, these two sources are travelling, the light from these two sources, these two coherent sources travelling the same distance. Therefore, they are in phase, and you have a bright fringe here, because there is constructive interference. Now, away from the center, there is a point here where the two waves interfere destructively, and therefore, the light is absent at that point. We have a dark fringe. So, we have a dark fringe here and a bright fringe here, and we have a pattern of this kind on the screen. So, let us try now to calculate the fringe width and the distance of the bright fringe and so on. So, for this, we have this construction. These are two slits whose distance is d, and the distance of the screen is capital D, and D is much larger. This capital D is much larger than this small d, although not clear from this diagram, but D is much larger than this d. And the light that goes here, the red ray and the blue ray, these two travel different distances from here to here, and from here to here they travel different distances, and therefore, the path difference or the difference in the distances that they travel to this point, the path difference is d sin theta, assuming that the d, this capital D is much larger than this d. This path difference can be approximated to d sin theta. So, d sin theta is the path difference, and this, if this path difference is equal to 1 wavelength or 2 wavelengths or 3 wavelengths, then there is constructive interference, because the phase difference is then 2 pi, and therefore, they as I have shown you earlier, that they are in phase. So, when d sin theta is equal to n lambda, the two waves are in phase, and therefore, we get bright fringe. And when the phase difference is pi, that is, they are in the opposite phase, one is going like this, the other goes like this, then there is destructive interference and we have dark fringe. So, the condition for bright fringe is d sin theta equal to n lambda, where n is either 0 or an integer, and the condition for dark fringe is d sin theta equal to 2 m plus 1 into lambda by 2, where m is an integer, again 0, 1, 2, 3, and this is the condition for dark fringe. It is important to remember that the width of the slits should be of the order of the wavelength or less. This is the condition for interference to take place, for the wave nature of light to be applicable. If the slit width is much larger than the wavelength of light, then we shall go back to our geometrical optics, and we shall get simply patches on the screen, not the pattern of bright and dark fringes. If the source of light is not monochromatic, say we take light from the sun, its white light consists of several colors, then you have colored fringes. The central spot will again, because all rays, I will show you later, all rays would travel the same distance to the central spot, therefore, all wavelengths, therefore, that would be a bright spot, but beyond that there will be colored fringes. Yeah, I have been saying that if this slit width is much larger than the wavelength, then we simply have patches of bright light on the screen. We do not have the fringe pattern. And we have seen already the conditions for dark and bright fringes. So, let us now find the distance of say a bright fringe from the central point of the screen. So, as long as y, the distance of the fringe from the central bright fringe, is small compared with d, this y is small compared with this d. Although this figure does not make it clear, but remember that this distance is much smaller than this distance, y is much smaller than d. That means, this angle theta is always a small angle. So, that you can say that tan theta is equal to sin theta is equal to y by d. So, you can make this approximation only when the angles are small, and then d sin theta is equal to n lambda, that is the condition for a bright fringe. From this we can write y, because sin theta is y by d. So, we can write the distance y equal to n capital D lambda by small d, that is the bright fringe, that is the distance of a bright fringe, nth bright fringe from the center of the screen. Similarly, the distance of the nth dark fringe from the center of the screen, that distance which I denote by y n d, d for dark and n for the number of the fringe, that is equal to n plus half into d lambda by d, capital D lambda by d. This is the distance of the nth dark fringe from the center of the screen. And if I subtract the distance of one fringe from the distance of the next, then I get the distance between the fringes, and that distance is delta y, distance between the consecutive fringes, say second and third or third and fourth. So, in this case I have taken n and n plus 1. This is the distance of the nth bright fringe, this is the distance of the n minus 1 bright fringe, and therefore, the distance between these two fringes is d lambda by d, that is the distance between these two bright fringes, it is d lambda by d. From the expression for the separation of fringes, it appears that the distance between the fringes is constant. You see, you might have noticed that this is constant, but this is always, remember, in the limit of small angles. You know, we have assumed that the angles are small, therefore, sin theta equal to tan theta equal to y by d. But if this approximation fails in a certain experiment, then the fringes will not be equally spaced. The fringes far from the central bright fringe, the small angle approximation may not apply, and the fringes may not be equally spaced. And this expression that the fringe width or the distance, you can use any one, say in a laboratory, to find the wavelength of light. We know d, we know small d, we can measure the distance between the consecutive fringes, say bright or dark fringes, and then we can find lambda, because lambda would then be d delta y by capital D. So, this is the basis on which the experiment is done in the lab to find the wavelength of light. An interesting thought: suppose that the whole double slit apparatus is immersed in a medium of refractive index mu. What would then happen? Suppose I am not doing the experiment in air, I am doing this experiment, interference experiment, in a space which is filled by a medium of refractive index mu. Then what will happen? You know, since the frequency of light remains constant, that is a fundamental property of light, that does not change from one medium to the other. What does change is lambda and the velocity. So, therefore, the wavelength lambda becomes lambda by mu. So, that the velocity is c by mu. You know, in a medium of refractive index mu, the velocity is c by mu. So, since the velocity has to become c by mu, wavelength must become lambda by mu, frequency does not change. So, what will happen? Then the fringe width, the distance between two consecutive fringes, would become d lambda by mu d. So, since mu is always greater than 1, delta y becomes smaller. So, the fringe pattern shrinks. If in air the fringes are this distant, then in a liquid, say water or a glass, but let us say, they might, the fringe width becomes smaller, the fringe pattern becomes shrinks. If you want animation of double slit interference, then these two, I have given these two websites where you can go and have you can see the animation of double slit interference pattern. Let us consolidate all that we have learned by a few examples. Example 1: a screen is placed at a distance of 1 meter from a double slit source. The distance between the two slits is 0.025 mm. You see, that is the kind of distance between the two slits d, small d, Remember, small d is the distance between the slits, and this must be very small compared with the distance between the slits and the screen. So, the distance between the two slits is 0.025 millimeter. The second order bright fringe is 4.0 centimeter from the central line. So, everything is given. So, you determine the wavelength of light. The distance of the second bright fringe from the center of the screen is given by 2 d lambda by d, the formula we just derived, and all that we need to do is to substitute the value of capital D, which is 1, small d, which is 0.025 millimeter, convert this into meters, and this is 4 centimeters, which is 0.04 meters. So, everything is given, just calculate lambda, and lambda comes out to be 500 nanometers. You can also get the fringe width delta y, which is capital D lambda by d. So, we have found lambda. So, we know d, we know small d. So, we can calculate what the distance between the fringes would be. It is 2 centimeters, not surprising. The second fringe is at 4 centimeters, and the fringes are equally placed. Therefore, the distance between them must be 2 centimeters. Take another example. A light source emits visible light of 2 wavelengths. We have a special source which emits lights of 2 wavelengths, 400 nanometers and 500 nanometers. The source is used in a double slit interference experiment, in which the distance between the slits and the screen is 1.0 meter, and the separation of slits is 0.030 millimeter. Find the distance between the third order bright fringe. The formula for the third order bright fringe is 3 d lambda by d. So, all that you do is substitute 1 lambda first for the distance, and then second lambda for the distance of that particular fringe pattern. Therefore, the distance between these two, the separation between these two sets, is 3 d by d into lambda dash minus lambda. So, if we substitute the values, you will find it is 1.0 centimeter. So, that is the distance between the third order bright fringes from the two wavelengths. And what are we going to do in the next lecture? Just a preview. We shall find the intensity of the fringes, and we shall also study the interference of white light. I have just shown you the figure here, given this is the preview, and the interference between light rays reflected from a plane surface. These are the 3 things that we shall do in the next lecture.